In this next subsection, we're going to look at fitting things to parabolas and cubics and other higher degree polynomials. Previously we were given 2 points, and that let us get a line, which is a 1-degree polynomial. In order to get a parabola, we have to have 3 points, and so that's 3 points for a degree 2 polynomial. So in general, if you're given n plus 1 points, and they have to have n plus 1 distinct x coordinates, there's a unique n-degree polynomial curve that passes through all of them. And I want to do an example here with a parabola. So it says find the equation of the parabola, and parabolas have this form that passes through these points here. So I'm going to do the same thing we did for lines, only now for each point I'm going to write the equation ax squared plus bx plus c equals y. I'm going to put the y on the other end there. So let's see, for 2, 1, I'm just going to replace each one of those x's with 2. So this will be 2 squared times a, so 4a, that'll be 2b plus c equals 1. Then for the point 4, 3, we're going to replace each one of the x's here with 4. So this will be 16a plus 4b plus c equals 3. And then this point, -1, 5.5, I'm going to replace each one of those x's with a -1. So -1 squared gives you 1a. Then you get minus b plus c equals 5.5. So this is our system that we need. Now, we've got to solve this system. I circled the whole thing, but the system is only these 3 equations. That top one is sort of a prototype. All right, so we've got to solve this, and I'm going to write it as an augmented matrix. So that's going to be the augmented matrix. Let's see, 4, 2, 1, 1, 16, 4, 1, 3, then 1, -1, 1, 5.5. So we've got to solve that, and I'm just going to use octave to do that. So I'm going to turn on octave down here. Now, we've been using octave online mostly in class, but what I'm going to do here is use octave installed on my computer. So I'm going to put that in. And by the way, if you're interested in octave, you can Google it, and it's a free program. So I'm going to put in this matrix, and I'm going to just call it M. M equals 4, 2, 1, 1. Bracket 4, 2, 1, 1, 16, 4, 1, 3, 1, -1, 1, 5.5. And so I'm just going to double check that that's all entered correctly. And now, of course, we want to row reduce it. And this is nice because notice it gives us, this is what's called an identity matrix. So I'm going to take that and let's see, move this over slightly. I'm going to take that and I'm going to copy it back onto here. So this row reduces to this is an identity matrix here because it's just ones along the diagonal and zeros everywhere else. And what we've got here is 1/2, -2, and 3. So what's nice about this is the identity matrix tells us that so A, remember our variables here are A, B, and C. So this gives us that A is equal to 1/2, B equals -2, and C equals 3. So that tells us our answer is going to be y equals 1/2 x squared minus 2x plus 3. Now let's test that. So originally the points we were supposed to have on this were the points 2, 1, 4, 3, and negative 1, 5.5. Negative 1, comma 5.5. Why is octave giving me trouble, or Desmos giving me trouble? Negative 1, comma 5.5. All right, so those points there, let me zoom in so we can actually see them. So there's a unique parabola, at least one that opens up or down, that passes through those 3 points. And it should be the one that we found up here. Let's put that in. Y equals 1/2 x squared minus 2x plus 3. And sure enough, that goes through all 3 of those points. One of them happened to be the vertex, it looks like. So that's an example of fitting 3 points to a parabola. All right, but we'll do the next example in the next video.